These notes cover what I call connected object problems. This is basically section 5.7 of the textbook. They call it, I think, interacting objects. Also, a little bit of what I'm going to cover today starts to push into a little bit of section 5.8. But anyway, let's get to it. All right, so there are these specific types of problems you might be presented with that look really hard but are actually pretty easy once you have the system down for how to deal with them. And here is the first of two different types of problems we're going to go over in these notes. So let's go over through the scenario, and then I'll end up with like the question we're going to ask. So I've got two objects, a 5 kilogram object and a 10 kilogram object, and they're resting on a frictionless surface. So we're just magically wishing away friction, because we can do that. Or you could imagine that they're on, rollers, but there's no meaningful friction. And you're going to be pulling these objects to the right. Another nice magical thing we can do in physics is we can pretend, or we can just make the ropes that we use to connect everything massless. That way we can ignore it. If these were real ropes, we would have to account for their mass, and we just don't want to do that. You are pulling on the lead rope with 45 newtons of force, and I'm going to call the tension in the rope because of your pull T1. And that's connected to the 10 kilogram object. Then on the other side of the 10 kilogram object is a second massless rope, and it's pulling the 5 kilogram mass along for the ride, and I'm going to call that T2. And the question is, what is T2? All right, so that is the question. What is T2? I'll tell you what it's not. And what some students want to do is they want to think, well, since you're pulling on this rope with 45 newtons, that's causing this rope to pull on this object with 45 newtons, which will cause this object to pull on this rope with 45 newtons, which will cause this rope to pull on this guy with 45 newtons. Okay, I hope you weren't listening to any of that, because that's wrong, okay? That's kind of like thinking, well, Newton's third law, Newton's third law, Newton's third law. Nope, that's not the right approach. Here is the specific approach that will always give you the correct answer. Step number 1 in this two-step process is determine the acceleration of the system of objects. You say, what the heck is a system of objects? Basically, we want to just think of these two boxes not as two individual boxes, but as a collection of boxes, or really just one thing. So just imagine that all of that stuff is just one thing. In other words, we're going to ignore the fact that there's a string between the 10 kilogram object and the 5 kilogram object, and we're just going to say, hey, you're pulling on a rope that causes the rope to pull on 15 kilograms of mass with 45 newtons. Okay, so that's what we mean by the acceleration of the system. So just to further kind of beat that point is we're just going to kind of imagine that we're pulling with 45 newtons on 15 kilograms of mass on a frictionless surface, and we want to know what the acceleration of that's going to be. And hopefully by now you think, well, that's a pretty easy Newton's second law problem. And it is, because we're given the force and we're given the mass. So here we go. So the acceleration of the system is going to be, think about what are the forces acting on my system of boxes, and divided by the total mass of the boxes. Okay, so let's get a frame of reference, as we always need one. Not a big deal here, but that's x. So this is going to be in the x dimension. Well, there's no friction, so there's only one force acting in the x dimension, and that's I'm going to call it the tension force. I'm just going to go ahead and say 45 newtons. That's what it is, okay? So we got 45 newtons pulling on 15 kilograms of mass, and that's going to be 3 meters per second squared of acceleration. Okay, that is the important first step in our journey towards finding out what is T2. Okay, because now step 2 is find T2. So step 2 is find the answer. determine T2. And that, just remind ourselves, is this guy right here. We want to know how hard is this rope pulling on the 5 kilogram mass. Okay, well, now we're going to take Newton's second law and we're going to kind of switch it around. We're going to basically say F equals ma. Let me just go and write that and say, well, okay, let me just write that. So basically, the forces on the x dimension equals the mass times the acceleration. But now the mass of what and the acceleration of what? Now we are no longer focusing on both boxes. We're just going to focus on the rear box. So let me draw that down here. So our focus now has definitely shifted to the last box. And we see that it's being pulled by the rope, and that's T2, and this is what we're after. So step 1, just to determine the acceleration of the system. Step 2, now we're in a position really to find the answer. What is the tension in this middle rope? Well, the tension in this middle rope is going to equal the mass, but now mass of what? It's going to be the mass of just, okay, well, I'm going to write it here, the 5 kilogram object times the acceleration of the 5 kilogram object. Well, what is the acceleration of the 5 kilogram? Okay, the mass is 5 kilograms. Okay, so that's going to be 5 kilograms. What's the acceleration? It's going to be the same as the acceleration of our system of boxes, right? Everything's going to be accelerating to the right at the same rate. And let me just be, since what is the forces in the x dimension on just the rear box? Well, that's our T2. So the tension in the second rope, or the rope to the left, is going to be equal to the mass of the rear box times its acceleration, which is the acceleration of our system. This is why we found the acceleration of the system, so that we could use it here. 3 meters per second squared. And that's going to be 15 newtons. Now, does that make sense? It's not 45 newtons. It's 15 newtons. And I think that makes sense. Let's see if we can see why. It took 45 newtons of force to make 15 kilograms accelerate at 3 meters per second squared. 45 newtons, 15 kilograms, 3 meters per second squared. Well, how much force does it take to make 5 kilograms accelerate at 3 meters per second squared? That's 15 newtons. All right, so this is an example of the type of problem where you've got things that are connected by these magical massless ropes, and you're asked to find the tension in some part of your system. Okay, this is the easiest one, but it's the same process even if it's like the third or fourth, even if you have like 3 or 4 boxes all connected together. And we'll do that problem at the very end here. Here's a second kind of problem, and it looks, let's go through it, but it looks a little different. You might say it looks very different, but essentially it's the same exact, substantively, it's the same problem that we just went over. But let's orient ourselves to what's going on here. I call these pushing problems. I still think of them as connected objects. I know there's no string connecting them, but there's got you got a group of objects, and you're pushing on, let me just back up. What the heck is going on here? Okay, we got 3 boxes on a frictionless surface. And now I got smart enough to label them box A, B, and C, and their masses are given. So box A is 10 kilograms, box B is 5 kilograms, box C is 15 kilograms. And all 3 of these are basically on a frictionless surface. And there is a push. Could be you, could be me, but something is pushing on box A to the right. I guess we need a frame of reference. It's a one-dimensional problem, but still need to think about what are we going to call forces, which was positive, which was negative, etc. Okay, it's a 6 Newton push. And the question is, this very specific question is, what is the force of box C pushing on box B? So I put that in a little cloud down here to kind of to make sure we understand exactly what the question is asking. It's not asking how hard does box B push on C to make it move. It's asking how hard does box C push back on box B while this is all going on. Now, if you remember Newton's third law, you realize this is a trivial complication because the force of box C pushing back on box B is going to be exactly the same amount of force as box B pushing on C. It's just going to be in the opposite direction. So what we're going to do is we're going to solve the actual answer that we're going to come up with when we calculate this. Is what we're going to figure out is how much force does B, looking for green here, how much force does B push on C, and then it's going to be the same amount, Newton's third law. Okay, so really what we want to figure out is how hard does box B have to push on box C to make it accelerate, given that all three boxes, in other words, are essentially being accelerated by this push to the left. It's the same exact process that we used here. Okay, step one, determine the acceleration of our system of boxes. So step one, determine a system of boxes. We're going to use that word system a lot in chapters on energy and momentum, a whole lot. This is kind of our first use of it. But for the beginning part of this problem, I don't really want to think of these as three separate objects. I just want to think of them as a clump of mass. And the total mass is going to be, we can add it in our heads here, 15 plus this, not 60, 30 kilograms of mass being pushed on by 60 newtons of force. And we want to know what the acceleration of this system of boxes is given this outside force. When we're doing that, we completely ignore kind of what's happening between the boxes. Okay, so it's the same kind of problem as before. So our, whoops, I don't like blue. Not for calculations, no way. So our acceleration of our system of boxes, again, I know maybe I'm belaboring this point, but I just want to make it clear. It's like, at this point, I don't care that there's three boxes. I just know there's 30 kilograms of mass and there's 60 newtons of force, making it, well, that's acting on it. And so what's the acceleration going to be? And there's no other forces, right? There's no friction in the horizontal dimension. We're completely ignoring what's going on in the y dimension because it doesn't affect what's going on. All right, so now we need to get all the forces in the x dimension on our system and then the total mass of our system of objects. Well, the only sideways force is going to be our 60 Newton pushing force, and the total mass, as we've already indicated, is 30 kilograms. So the acceleration of our system of boxes is going to be 2 meters per second squared. Okay, there's only one and only one reason that's not the answer. Why did I put the second? Don't put the second one down there. Just put the first. One blue meaning, okay, so the one blue, it tells me, hey, that's important, but that's not the answer. Okay, now we are ready to, maybe you can anticipate what we're going to do already. We're going to now think about box C and only box C. I guess that's actually right down here, but I'm going to draw it again. So we shift our focus is no longer on this system of three boxes. It's now on box C, which has 15 kilograms of mass, and its acceleration. So its acceleration is going to be 2 meters per second squared. And now I just want to know, is what force will B have to exert on C to make it accelerate at 2 meters per second squared? Newton's second law problem. I'll say one more time. We're doing exactly the same thing as we did on the previous problem. Now, Newton's second law. Oh, let's do it. Let's say determine force of B on C. Okay, well, the force of B on C is going to equal the mass, Newton's second law, is going to equal the mass of C times the acceleration of C, which is going to be equal to the acceleration of our system. This is the entire reason why we determined the acceleration of the system, because these two accelerations are going to be the same. So now it's a fairly trivial problem. We've got 15 kilograms of mass accelerating at 2 meters per second squared, and that's going to be 30 kilogram meters per second squared, but we know a kilogram meter per second squared is really a newton, so that's going to be 30 newtons. Now, I'm going to argue that that's not the answer, even though that is the answer. You say, well, what do you mean that's not the answer? Well, this is the force of B pushing on C, and the problem specifically asks us what is the force of C pushing back on B. But it is the answer in the sense that what is, well, Newton's third law. What is force of C on B? This is the magnitude only. I'm not worried about direction. Just how hard is C? Well, these are going to be the same in magnitude. All right, Newton's third law. Force of B on C equals negative, but again, I don't want to focus on the negative right now because we're only asked how hard. That's a magnitude only. I don't care what direction. We know that C is going to be pushing to the left. If B is pushing to the right, C is pushing to the left. But Newton's third law, stated in all of its glory, is force of B on C is equal minus force of C on B. So basically, the force of B on C, force of C on B, magnitude only. That's what these absolute, well, hey, I didn't even put the vector sign. That means, so if you have the vector sign on top and the absolute value signs, that's magnitude only. Okay, whatever. I haven't been putting vector hats on here, and just so it's magnitude. Magnitude only is 30 newtons. Okay, it's the same. Now that is the official answer. That is the answer. But I forgot to ask, does this make sense? That's kind of something I haven't done a good job this year of showing to you. Like every time you come up with an answer, you should kind of glance back and say, well, does that make sense? If you come up with like, the softball came at the batter at 1.6 million miles an hour. Okay, well, that doesn't make sense. Okay, so does this make sense? We say 30 newtons. Let's go back to our original figure here. We're claiming that C is pushing on B with 30 newtons because B is pushing on C with 30 newtons. We'll notice that that's half of the outside pushing force. I think it makes sense because if we look at how does the mass of C compare with the mass of the total? And so we have 15 kilograms compared to a total of 30 kilograms. So we can see that object C is half the total mass. So that means the force that B pushes on C and C pushes back should be about half of the total force, right? You got half the mass accelerating at the same rate. Well, that's going to take half the force, and that's what we come up with. So I think the answer does make sense. This last problem that we're going to go over looks almost impossible to solve, but it turns out it's actually easy to solve once you know how to look for it. So what's going on here? Again, we're going to have a no friction surface. We just don't need to worry about friction. So friction, no. We've got 8 identical cars, little carts, what have you, all connected by these magical massless strings. Now, are they truly, there's no such thing as a truly massless string, right? But what we're saying basically is that the mass of these carts is so big compared to the mass of the strings that they don't matter much. Again, we've done that many times in physics. So, the idea is we only consider those things that have a meaningful effect. And so the mass of these strings, they're never going to be truly massless, but we're just saying basically is the mass of the strings connecting these carts is so tiny compared to the mass of the cart. So, for example, these might be like 100 kilograms each, and this would be, a tenth of a kilogram or something like that. Okay, so we've got 8 of these carts. They all are identical, mass m, and they're all on a frictionless surface, and they're being pulled by a 2,000 Newton force. So we know that in the x dimension, well, it's not the x dimension until we make it there. Now it's the x dimension. Is going to be accelerating in the positive x dimension. And we're being specifically asked is what is the tension between the second and third car? And you go, oh my goodness. Okay, so you go back and say, well, we'll do the same thing that Mr. McIntyre said we should do is we're going to determine the acceleration of the system. We need to know the forces on the system and the total mass. And you're going to go, but we don't know what the mass is. All we know is that it's 8 times m. All right, so here's how you deal with these kind of problems. And it is essentially the same. Anyway, this is exactly, so we want to know, what is this tension force here? Let me find the color. What am I looking for? Black. Okay, so we're not going to know what the acceleration is of this mass, of this 8-car little train. We can't come up with a number, but what we do know is that the acceleration of the last part of the train, which is these guys, is going to equal the acceleration of the entire train. So I'm going to say the acceleration of 1 plus 2. By that, I'm talking about these guys right here. So the acceleration of this last part of the train, which I'm calling basically 1 and 2, is going to equal the acceleration of the entire train. Or, yeah, I'm starting to call it a train now. Okay, that is a true statement. Now, what can we do with that? How are we going to get tension out of that? Well, remember that acceleration is equal to the forces. So this is the x dimension. Acceleration in the x dimension equals what are the forces in the x dimension divided by the mass of the object. So what are the forces? So basically we're just going to apply. Well, let's do this. Let's be a little bit more formal about it. So what we're going to think about is the sum of the forces acting on 1 and 2 divided by the mass of 1 plus the mass of 2. That's basically Newton's second law. That's, of course, this is going to be the tension force that we're interested in. For the entire system, it's what is the outside force on the entire system? That's going to be this 2,000 Newton force divided by the total mass of the entire system. Okay. This is kind of cool because you can see, and these are the kind of problems that the AP exam likes to ask because it's not about number crunching. Okay, so this is a problem. There's no numbers here, but we'll still get the answer. Well, there's two key numbers. All right, well, what is the sideways force acting on the rear part of the train? Well, that's the tension that we're asked for. Let's go back and say that's T1 plus 2, the tension on cars 1 and 2. So that's going to be T1 plus 2, that's actually what we're asked for. And then the total mass is going to be m plus m, that's going to be 2m. And what is the force, the outside force acting on our system? It's going to be this 2,000 Newton. So I'm going to go ahead and just write that. 2,000 newtons. What's the total mass? We don't have a value for it, but we can represent it. It's basically 8 of these m's. Well, what is 8m plus m 8 times? Do that, add it 8 times. Well, that's 8m. Okay, so let's go ahead and shift. Let's solve for T1 plus 2. We can see we can solve for it now. So the tension pulling the last 2 cars is going to equal I multiply both sides by 2m. So I get 2m over 8m. I'm just doing a little. So if you didn't follow that, basically I just multiplied both sides by 2m. I just decided to take the 2m divided by the 8m here and put it here because I want to emphasize this ratio thing. Okay, well, we see that the m's cancel. And so the result is that the tension in the last, well, between cars 2 and 3, the tension that's pulling the last two cars equals 1/4 of the external pulling force. Now the answer is 500, right? But that's not the important part. The important part is to represent, this is the key part. Is that if you want to know the tension, you're pulling a series of objects and you want to know the tension force in between any two of the objects, your answer is going to be what is the outside force times the ratio of the mass, I'll say in this case to the left. I mean, if you're pulling to the left, it could be to the right, but the mass, the mass behind divided by the total mass. So here we had, so basically this string right here between cars 2 and 3 was pulling only 1/4 of the total mass. So this tension force was 1/4 of the total. Let's see if we can play around with that, and without doing a lot of calculation, just play around and get some answers. I'll write them in green. Okay, so here is halfway between. Guess what the tension force is between cars 4 and 5? Well, this tension force between cars 4 and 5 is pulling half the mass, half of the total mass. So its tension force will be half the total. And hopefully that makes sense once you know how to look for it. Let's try this guy right here. Now, no, well, we've already done this one. So let's go back and say, okay, this one is 500. Okay, what about this one right here? It's pulling, this poor little rope here is pulling 3/4 of the mass. So it's going to be 3/4, the tension force will be 3/4 of the total. Well, that's 1,500 newtons. Okay, what's this one going to be? Is it going to be a hard one? Well, this is going to be 1,750. This one will be 1,250 newtons. This one, what's this one? Let's see if we can do this one. Okay, this is only 1/8 the mass. So this string is pulling 1/8 of the total mass. So what is 1/8 of 2,000? It's 250 newtons. All right, so that's how you deal with problems when you're just given masses, okay, and not numbers. If you're given the numbers, you could do the same approach actually, but you could also do the number crunching. Here, you just have to think more about the approach here. All right, those are the notes. I've also posted answers on Canvas, so hopefully that will equip you to do this set of homework problems.